This is AP Calculus 5.2, the extreme value theorem. In the extreme value theorem, we're talking about the absolute or global maximum and minimums, and we're talking about the relative or local maximum and minimums. And the extreme value theorem is an existence theorem. It tells us that there will be a maximum and a minimum value within a closed interval. The extreme value theorem states if a function f is continuous over the interval or the closed interval AB, then the extreme value theorem guarantees that f has at least one minimum value and at least one maximum value on the open interval AB. So in symbols, that would mean that f of c, if f of c is greater than or equal to all f of x values, then f of c would be a maximum. So if f of c is greater than or equal to all f of x values within the function f, then f of c would be a maximum. If f of c is less than or equal to all f of x values within the function f, then f of c would be considered a minimum. Within the calculus curriculum, we need to understand the difference between what is a relative and what is an absolute maximum and minimum. A global maximum or minimum is an absolute, or the absolute highest or lowest point on a given graph within that closed interval. A local maximum or minimum is where the curve changes and it appears that it's a maximum or a minimum based off of the graph, but it's not the absolute highest or lowest point on the graph. So an example of that, if you have a graph that looks something like this, I'll just do a real simple drawing. Let's say that that's the shape of our graph. Right here and right here, we have a local maximum here and a local minimum here. In other words, the graph has a curve or a horizontal tangent line at those points, but because this graph continues forever in the downward direction here and forever in the upward direction here, these are not the absolute highest and lowest points or the global maximum or minimums. They would just be the relative or local maximum or minimums, because all of the points below this would be considered lower than this local minimum, and all of the points higher than this point would be considered higher than the local maximum here. So you can't say that these two are global or absolute maximum and minimums. They would be local or relative maximum and minimums. We refer to global maximums or absolute maximums when we have a closed interval. So I could take a graph that's very similar to that, and I could say, okay, now here is my graph, but this and this are the highest and lowest points because we're dealing with a closed interval from A to B. So within this closed interval, right here and right here, these would be considered relative or local maximums and minimums. But the absolute maximum would be here because it's the absolute highest point on that closed interval. And the absolute or global minimum would be here because that is the absolute or global lowest or minimum point within that graph. So there's a big difference between a global and a local maximum or minimum, and an absolute or a relative maximum and minimum. Here it says find the global and local maximum and minimums if they exist. And it says the following is a graph of f on a closed interval A to E. So we've got a closed interval going from A to E here. So we have a global minimum right here at the very lowest point on this interval, and we have a global maximum right here because that is the absolute highest point on this graph. We do have some relative or local maximums and minimums. This point right here would be a local maximum because it's a peak, and this right here and this right here, the end point, would both be local or relative minimums because they are at valleys. This one right here is at the end point. It's a relative minimum because that's the lowest point for that portion of the graph. A critical number is any x value of a function where the derivative is 0 or undefined. And there are a couple things we need to remember for this. The derivative is 0 at all of your maximum and minimum values because the slope of the tangent line will be equal to 0. So if you think about what a function looks like, if I just graph a very simple function, right here we would have a relative minimum, and right here we would have a relative maximum. Since the slope of the tangent line there is at 0 or it's horizontal, those would be considered critical values or critical numbers. We also need to consider numbers being critical when the derivative is undefined, and that happens, we have an undefined derivative when we have vertical tangent lines, discontinuities, and sharp turns in the graph. So if we go back and look at this function again, it would have horizontal tangent lines here, here, and here. So those would all be critical numbers. It would also have a horizontal tangent line right here and right here. Those would also be considered critical numbers. This particular graph didn't have any sharp turns or discontinuities, so we can't identify any other critical numbers from this graph. But if we look at some other graphs, we may be able to. So if we know that a critical number is any x value of the function where the derivative is 0 or undefined, if they give us a function and ask us to find the critical numbers, the first thing we have to do is take the derivative of the function. Now for this function right here, it's going to be easiest to take the derivative if I first rewrite it. So I'm going to rewrite that function as f of x equals x cubed minus 3x squared. Then I'm going to take the derivative. F prime of x is equal to 3x squared minus 6x. Then to find the critical values, I'm going to set that function equal to 0, and I'm going to try to determine if it has any undefined spots in that function. And in this one, there is nothing there that's going to be undefined because it doesn't have a denominator. So there will be no undefined values here. But it might be equal to 0. We can determine that if we factor this function. So I'm going to take out a 3x. When I do that, I have x minus 2 left. And then I'm going to set each factor equal to 0. So here I would have x equals 0. And for this one, I would have x equals 2. So that means I have two critical values. Those critical values are at x equals 0 and x equals 2. For the next one, to find the critical values, I'm going to do the same thing. I'm going to take the derivative of what I've got here. I'm going to use the quotient rule. F prime of x equals 2x minus 3, derivative of the first thing, times the original second, x squared minus 4, minus the original first, x squared minus 3x minus 10, times the derivative of the second thing, which would be 2x, over the denominator squared. If I simplify that a little bit, I could FOIL these. That would be 2x cubed minus 3x squared minus 4x plus 12. If I distribute a negative 2x here, I would have a minus 2x cubed plus 6x squared plus 20x. If I add those like terms on the top, the 2x cubes cancel. 6x squared minus 3x squared is a 3x squared. Negative 4x plus 20x is a positive 16x. And then a plus 12. And that is still over my denominator, x squared minus 4 squared. And then I could look and see if these would factor at all. 3 times 12 is 36. Are there factors of 36 that add to give me 16? And there are no factors of 36 that add to give me 16, so it's not factorable. So if I'm trying to find the critical values of this function, the first thing I need to do is set the numerator and the denominator equal to 0. I'm setting the numerator equal to 0 because those would be the points where the derivative of the function is equal to 0. I'm setting the denominator equal to 0 because those would be the points where the function is undefined. So if I set the numerator equal to 0, we've already established that it's not factorable. So I could do this on my calculator. I could use the equation menu on my calculator to solve that. So that's what I'm going to do. I'm going to my calculator. I'm going to go to an equation solver, a polynomial equation with second degree, and my a, b, and c values will be 3, 16, and 12. And when I solve that, I get two places where the function is equal to 0. And I could establish these on using the quadratic formula as well. That would be a -8 plus or minus 2 square root of 7 all over 3. That's what the quadratic formula would give me. And those x values for as decimals would be at x equals -0.902 and x equals -4.43. And sometimes you're going to have messy values like that for your critical values. So these would be my two critical values from the numerator. For my denominator, to find my critical values, all I'm going to need to do is set that denominator equal to 0. So if I do that, x squared minus 4 squared equals 0. Well, if I take the square root of both sides, I have x squared minus 4 equals 0. And then if I solve that, x squared equals 4. If I take the square root, I would have x equals plus and minus 2. Those are my other two critical values for this function. So I have 4 critical values based off of that second function. So to find the critical values, the first thing I do is take the derivative of the function, and then I would set the derivative of that function, the numerator of that equal to 0, and the denominator equal to 0 to get my critical values. For the third example, if I'm trying to find the critical values, the first thing I'm going to do is take the derivative. I'm again going to use the quotient rule. So the derivative of the first thing is a 4 times the original second, x squared minus 1, minus the original first, 4x, times the derivative of the second or the bottom would be 2x, and that's all over the bottom squared, x squared minus 1 squared. To find the critical values, I'm going to set the numerator and the denominator both equal to 0. So if I take this numerator, if I distribute it out, I would have 4x squared minus 4 minus 8x squared. And I'm going to set that equal to 0. And then the denominator set equal to 0, x squared minus 1 squared equals 0, would give me the places where my derivative is undefined. So for this one, 0 is equal to -4x squared minus 4. If I divide everything by -4, I'll have 0 equals x squared plus 1. So I end up with x equals plus or minus I. Well, I can't have critical values that are imaginary, so the numerator is not going to yield any critical values. For the denominator, if I take the square root of both sides, I have x squared equals 1, and so x will equal plus and minus 1. So my two critical values, and they happen when the denominator is set equal to 0, my two critical numbers are at plus and minus 1. And if you think about that, isn't that going to be where the original function had two asymptotes? If the function is undefined, those values become critical because you can't take the derivative at those values. Next, they may give you a graph and ask you to determine where the critical values are, and that's really simple to do. For this graph, and this is the function, f of x equals the absolute value of x squared minus 4x plus 3. The critical values are anywhere that you have a horizontal tangent line. So right here we would have a critical value at x equals 2, or where you have a sharp turn. We would have sharp turns at x equals 1 and x equals 3. So you have three critical values here at x equals 1, x equals 2, and x equals 3. For the next one, we have critical values anywhere you have a horizontal tangent line. So right here, and then there's another horizontal tangent line right there. So we have three of them at x equals -2, at x equals 0, and at x equals 2. Here we have critical values anywhere you have a horizontal tangent line. The horizontal tangent line is here at x equals 1. We have another horizontal tangent line here at x equals 6. And then anywhere that the derivative is undefined. Well, that happens when you have a break in the graph. So we have another critical value at x equals 3. We have another critical value at x equals 5 because that's a sharp turn. And then we have a vertical tangent line here at x equals 4. So that would also be a critical value. So this one happens to have 5 critical values. Looking for the critical values here, go ahead and pause the video and see if you can figure out where the critical values are for these functions. In the first one, we've got a sharp curve at -1, so it's not differentiable there. And we have horizontal tangent lines at 0, 2, and 4. So it has 4 critical values. For the next one, it's not differentiable at 2 because of the sharp curve. It's got 2 horizontal tangent lines at 0 and 1, so those would be our critical values. And then for the third one, there's an asymptote at x equals -2 and a hole at x, what appears to be x equals 3. Now we can't tell exactly, but I'm going to estimate that that's at x equals 3. So we have 2 critical values, x equals -2 and x equals 3. Here I have a graph on a closed interval, and the directions are asking you to find all critical values and global and local maximum and minimum values. Well, my critical values would be where the derivative is undefined or where the function has a horizontal tangent line. So my critical values would be at the point B, at D, at E, and at F. Critical values, remember, are where the derivative is undefined, so right here and here, or where the derivative has horizontal tangent lines. So that would be at E and at F. We do need to consider C right here. That's a very gradual difference there, and basically what that is it's a point of inflection. And what we're going to learn later in the chapter is that where you have points of inflection, you have a change in concavity. And what this is actually showing you is another horizontal tangent line right here. So C would also be considered a critical value, but it looks a little different in this graph, so I wanted to make sure I pointed that one out. So I should have a C in there as well. Where are your local and global maximum and minimum point? Well, the global maximums and minimums are going to be where the absolute highest and lowest points are on this graph. So my global maximum here, the highest, absolute highest point on my graph is B. But the global minimum has a problem here. I would say that my global minimum would have to be at D, but this is an open circle at D. So we can't say that that is the global minimum because it's an open circle. And since we can't determine exactly where these points are right beside D, we have no global minimum in this one because we can't identify where the absolute lowest points are. So this one has a global maximum, but no global minimum because of that special case there with an open circle. We do have some relative or local maximums and minimums. The local maximums would be at E and at, we could consider G a local maximum. Your local minimums would be at A and at F, but we can't identify a local minimum at D since, again, that's at an open circle. For this one, the critical values need to be identified, and I want you to identify your global and your local maximums and minimums. So go ahead and pause the video, see if you can find those things for this graph. Here are the answers for this one. I would say there are critical values at anywhere you have a horizontal tangent line, so at B, at D. E is critical because it's a sharp turn, and F, that's hard to say whether that's a sharp turn. I would say that's a sharp turn there because it goes from a straight line to a curve, and anytime that happens, that would be considered a sharp turn. If this had been more of a curve for both of them, I would say that it was critical because of the horizontal tangent line. You have global maximum nowhere on this one because the absolute highest point here would have been G. You can kind of see that if I draw a line. So the absolute highest point is this point right just below G, but we can't tell what that is because G is an open circle. So it has no global maximum. It has a global minimum down here at A because it's closed in. Your local maximums would be at B and at E, and your local minimums would be at D and at F. For this one, finding all critical values. Well, the only critical value here is at x equals 0 because that's the only place we have a horizontal tangent line. Finding local and global maximums and minimums. This one would have none of either because since this is on an open interval, we can't identify exactly where the local maximum or global maximum or the local minimum or global minimum is. The absolute highest point would only be this point just below that open circle, and the absolute lowest point would only be this point just above this open circle. So there's no way to identify where the global or local maximums and minimums would be for this graph. Here I've given you a function, and I want you to answer, does this have an absolute maximum or minimum on the closed interval 2, 6? You need to understand how to do this algebraically as well as graphically. So I'm going to show you algebraically first. Basically, to find the absolute maximums and minimums, we have to consider the entire graph. And we have to consider where the graph has critical numbers. And when we do that, we have to find an XY chart for all of those critical numbers and see what's happening with the Y values there. Where we have our critical numbers are the possible places that we could have our absolute maximums and minimums or our global maximums and minimums. But we also have to consider the endpoints of this equation because sometimes your endpoints might be the absolute highest or lowest point on the function. So the first thing I'm going to do here when I'm doing this algebraically is I'm going to have to find my critical numbers. So I'm going to take that function and I'm going to find the derivative. If I find the derivative of the top, that would be 2x times 9 times the original bottom, which is x cubed, minus the original top, 9 times x squared minus 3, times the derivative of the bottom, 3x squared, all over the bottom squared. So that would be x to the 6th. And so then if I just simplify this a little bit, right here I have 9 times 2x times x cubed is 18x to the 4th. And then I'm going to distribute a negative 27x squared here. So that would be a negative 27x to the 4th plus 81x squared. And that's all over x to the 6th. If I simplify that a little bit, 18 minus 27 is negative 9x to the 4th plus 81x squared all over x to the 6th. And all of those are divisible by x squared. So I can simplify that to negative 9x squared plus 81 all over x to the 4th. So now if I set the numerator equal to 0, negative 9x squared is equal to negative 81, and then x squared would be equal to 9, so x equals plus and minus 3. So I have two critical values at positive and negative 3. And then if I set the denominator equal to 0, x to the 4th equals 0, that would yield another critical number or critical value at x equals 0. Now, if you think about this one, and look at what we had originally here, if I were to graph that, hopefully you understand there would be a vertical asymptote at x equals 0. That's what makes this a critical number. That's where the function is going to be undefined, or the derivative is not going to exist at those places. So we have three critical values at x equals plus or minus 3 and at x equals 0. And so if we're trying to figure out where our absolute maximums and minimums are algebraically, what we would do is we would take these values, we would put them into an XY chart. So if they don't ask us to graph it, they just ask us to find the maximum and minimum values based off of the critical values within a closed interval. We're going to take this closed interval and we're going to take all of these ordered pairs, and anything within this closed interval is what we're going to consider. So now, -3 is a critical value of this function, but it's not within this interval, so we don't have to even consider it in our chart. So we're going to consider 2 to be the lowest x value in our chart that we're going to consider. 3, again, x equals 0, that's not even considered in our chart because from 2 to 6, that's the closed interval, and 0 is not within that interval, so we don't even need to use that one. We're going to consider 2, 3, and 6 using this closed interval. So I'm going to make an XY chart using 2, 3, and 6. Then I'm going to plug these values in to my original function and see what I come up with. Now, use your calculator for that computation. There's no need to try to do this by hand. If I plug a 2 in, I end up getting a 1.125 for my y value. When I plug 3 in, I get 2, and when I plug 6 in, I get 1.375. So if they're asking us to find the absolute maximum and minimum on a closed interval like this, my absolute minimum is going to be at the lowest y value. So my absolute minimum is going to happen at x equals 2. My absolute maximum is going to happen where my y value is the highest. So that happens at x equals 3. Okay? Now, if we look at this considering the graph of this function, I've got the graph right here. Remember, we're only considering what happens from 2 to 6. So if we're just looking from 2 to 6, this is the portion of the graph that we're looking at. Well, it looks like my lowest value at 2 is going to be at the number 2. So it looks like that is my minimum of the graph. It looks like the highest point on my graph would be right here. And so we would need to do a little bit of algebra to tell exactly where those points are, which we did here. And we can see that the minimum happens at 1.125 and the maximum happens at 3. So this must be at 1.125 and this must be at 3. And I generated this graph using Desmos. So if you were at Desmos, then you could actually tell exactly where that point is if you were actually in that function. So that would be a way to do that. Looking at the next one, this one's a little bit easier when we're considering a closed interval. To find the critical values, again, we're going to take the derivative. F prime of x equals 12x cubed minus 12x squared. To find the critical values, I'm going to set that equal to 0. There are no critical values based on the derivative being undefined because the derivative here has no denominator. So that makes this one a little bit nicer. I'm going to take out the negative 12x squared that they have in common to factor it, and I've got x minus 1 left. So if I set each of those factors equal to 0, I get a double root at 0, or a double factor, I could say, at 0. So that's a critical value at 0 and another critical value at 1. So I'm going to do my XY chart, and both of these are within the interval that they gave me. So I'm going to set up an XY chart using the endpoints. So at -1, 0, 1, and 2, those are the ordered pairs I need to identify. When I plug these numbers in, and again, I'm going to use my calculator to do this, I'm going to plug the original function, 3x to the 4th minus 4x cubed, into my table menu, and then I'm going to plug those values in. At -1, I get 7. At 0, I get 0. At 1, I get -1. And at 2, I get 16. So if I'm trying to identify my absolute maximum and minimum values here, or my global maximum and minimums, my global maximum would be at 216, and my global minimum would be at 1, -1 within this interval. It is very important to understand that when you're asked to find global or absolute maximums and minimums on a closed interval, that in your chart you include the values at the endpoints. If you don't, you may miss those global maximum and minimums, and you may use these 2 points. Let me show you why. Here's a graph. I can't tell from -1, I can't tell exactly where that's crossing, and at 2, I can't tell where that's crossing. So I need to look at this a little bit further if I use a better graph here. Notice at -1, if I'm using Desmos, I can click here. I know that at -1, I'm at 7. At 2, I'm at 16. If I don't consider my endpoints, then I may look here and identify my maximum and minimum based on these points here. But I know if I'm asked to find a global or an absolute, then I'm looking within this closed interval. And when I'm looking at that, my absolute maximum is at 216. My absolute minimum is here at, I believe that's at 1, 1. Is that what I'm sorry. That is at 1, -1, which is what I found here. So I'm getting the same thing looking at the graph, but if I don't consider my endpoints, then I may have looked at this graph and thought my maximum was at 0. So I have to be real careful.